All right, guys. Sorry, we're starting the video a little bit late today, but we took a couple seconds, and if you're watching the video, you're going to pause and take a couple seconds and do this investigation. So pause now, try it out. We started the first question here. We were just discussing the period of the functions above and the number of cycles that fit between 0 and 2 pi. Okay, so like I said, number of cycles that fit between 0 and 2 pi are going to be actually equal to the k value. And then the period, does anyone remember, if I know what the k value is, does anyone remember how we can calculate the period of a function? Alexandra? 2 pi over k. So if I'm actually looking at the equations here, we could have calculated that one of two ways. We could have looked at the graph and determined how many cycles, like what the length of one full cycle was, or because we know the k values, we could have actually just calculated with that little formula. All right, so we also just did a brief discussion on where sine x was equal to 1 over root 2, or 0.71, and those are the green points that we labeled here. So how many solutions do we have for sine x equals 1 over root 2 between 0 and 2 pi? We have 2 solutions for that. And how about for our graph of sine 2x? How many solutions are equal to approximately 0.71 between 0 and 2 pi? There are 4 solutions. So 1, 2, 3, 4. We can see this is about 0.75 here, so 0.71 is happening maybe like right below there. So this one has 4 solutions. Okay? And we know that when we have sine of 2x, that gives us a k value of 2. What is the actual transformation that is occurring when I have a k value of 2? Okay, it's a horizontal compression by a half. So I have actually taken my period and I've halved it, right? What used to fit between 0 and 2 pi now fits between 0 and pi. And I have double the number of cycles between 0 and 2 pi in my sine of 2x graph, right? I've compressed it by a factor of half. So what normally fits between 0 and 2 pi is now doubled in that range. So when I cut the period in half by making my k value equal to 2, what happens to the number of solutions between 0 and 2 pi? So the solutions will be more, yes, but approximately how much more? What happened to my number of solutions here when I halved the period? They doubled. Okay, so when my k value is 2 versus 1, my number of solutions here is actually doubling. Alexandra? Yeah. So the number of solutions has doubled. Can I ask you guys, if I made my k value 3, what do you think my number of solutions would do? So I would have gone from 2 to 6, which is what? How have my solutions grown? To get from 2 to 6, I multiply by 3. So I'm tripling my number of solutions, right? So depending on what your k value is, if I compress the graph, I'm going to get more solutions within 0 to 2 pi by a factor of k. So if my k is 2, I'm going to get double the number of solutions that I would normally have between 0 and 2 pi. If my k value is 3, I'll get triple the number of solutions between 0 and 2 pi. If my k value is 4, what's going to happen to my number of solutions between 0 and 2 pi? It will quadruple, right? Yeah, exactly. So we don't always have 2 solutions for everything between 0 and 2 pi. We usually do. But if it's like 0, 1, or -1, sometimes we have a different number of solutions between 0 and 2 pi. Sometimes there's 1, sometimes there's 3, sometimes there's 2. So we have to kind of look at that. Okay, so this leads us to our new type of questions, which are called double angle questions. We've been working with double angle identities previously in this unit. So we talked about how like the sine of 2x is equal to 2 sine x cos x. Now we're being asked to solve for where sine of 2 theta is equal to a half between 0 and 2 pi. So the regular graph of sine x, we're actually just going to look up in our investigation here. Now we're actually going to solve this as well. But if I look up at my graph, how many times does sine x, this first graph here, hit 0.5 between 0 and 2 pi? It hits it twice. It hits it here and here. Agreed? Yes. Now how many times does the sine of 2x hit 0.5 between 0 and 2 pi? Jonathan? 4. 1, 2, 3, and 4. So I should expect, if I do this correctly, I should expect to get out 4 answers. They're going to be kind of like, I'm not sure exactly where those are on this graph, so we're going to kind of have to figure out where those exactly are. Okay, so I'm going to show you how we'll do this mathematically. Usually what I like to do is I'm going to just start with a little let statement, and it's going to be let 2 theta equals some value. It doesn't matter what that value is. We can say x, we can say r if we want, any variable. So maybe we will let 2 theta equal j. Yeah. Me, Jeremy, Jonathan. Jolie. It's for you guys.
We're officially the best students in this class.
Totally. Yep. Okay. So the sine of some value is equal to a half. You guys know how to solve something like this, right? This is all of what we did yesterday with our linear trig equations. We're going to go through the decision process. Okay? So my first decision I want to make is, can I use a graph to solve this? I mean, we did kind of use a graph to solve it above, but typically, do we know where sine is equal to a half off by heart on the graph? Probably not, right? So we said we can use graph when we have, I know, but you have the graph written out for you, like already graphed out for you. So typically, we probably won't know where that is, so we'd probably go no on that one. Can I get opposite over hypotenuse of 1 over 2 from a special triangle? Yeah, we can. The pi over 6, pi over 3 triangle, right?
No, we have pi over 6, pi over 3.
Right. Okay, which angle is going to give me an opposite over hypotenuse of 1 over 2? Yes, pi over 6 will give me an opposite over hypotenuse of 1 over 2. That's going to be our reference angle, which is pi over 6. Okay, I also, again, want to consider the cast rule, so very similar to what we just did in our warm-up question. Using my cast rule, I have 2 quadrants that will give me sine of an angle equal to a positive value. What are those quadrants? Pierce, go ahead. 1 and 2, all and sine. Awesome. Okay, so I'm going to have J1 and J2. Keep in mind I actually want to solve for theta here. So once we solve for J, we're not really done yet. What is J1? Pierce? Pi over 6. And that means that this little reference angle over here is also equal to pi over 6. How do I calculate J2? Sam?
Pi minus pi over 6.
Pi minus, good. Pi minus pi over 6. So I want to go all the way around here, but less pi over 6, like just before I get to pi, right? So we want to subtract. So that is going to give us, once we find a common denominator, that's going to give us 5 pi over 6. Okay, now these are not my answers. These are going to help me get my answer, but they're not my answers. I'm looking for theta. And we used a let statement. So we know whenever we use a let statement, we did this in logarithms as well, we must plug back into that let statement and actually make sure that we're solving for what we're supposed to solve for, right? So I'm going to plug my j's back in here. Okay, I'm going to have to do that twice, and I want to solve for theta. Okay, so if 2 theta equals pi over 6, J1, I divide out 2, and that's going to give me pi over 12. We'll call that theta 1.
Wait, how do you divide out 2 if pi over 6 is already a fraction?
So if I have pi over 6 over 2, think of that as 2 over 1, and then I'll have pi over 6 times 1 over 2, and that gives me pi over 12. Okay, I'm not going to show that math. I trust that you guys can do the flip and multiply. So yeah, that's really what we're doing. Okay, so that's going to be my theta 1. I also know, I'm going to box that guy up. I also know that this 2 theta is equal to 5 pi over 6. So what is my second theta going to be equal to here? Alexandra? 5 pi over 12, you got it. And this is radians, so we'll just put rad next to that. Okay, now what about my other 2 answers? Because we said we were going to have 4 answers here, right? We actually even marked it off on the graph. We said there were 1, 2, 3, 4 answers. I just found the first 2. Any ideas for how we can find the next 2? How long does it take me to get from this point to this point? Jonathan?
Pi.
How do you know that?
Because of the period is pi, and by the time the cycle repeats, then
Yeah.
the answer is just period.
At this point in the cycle, if I go from here all the way back up to here, that's 1 full cycle right there. We know for that particular function, we've already found the period of that function. It was pi. So if I take my answer and I simply add the period to that, I will get from here to my next answer, which will be here. And then if I take my second answer, which was this guy, and I add the period to that, I'm going to get my next answer. Okay? So all we need to do to get those last 2 answers is simply add the period of the function. So here, the period of our function Okay, here the period of our function, I can calculate using that k value, right? So we said period is always going to be equal to 2 pi over k, and in our case it's 2 pi over 2, leaving us with a period of pi. So I'm actually going to take my theta 1, and I'm going to add pi to that, and then I'll take my theta 2 and add pi to that, and that will give me theta 3 and theta 4. Okay? I know that there's no more than theta 3 and theta 4, or actually let me ask you that. How do I know, if I didn't have the graph, how do I know that there's going to be only 4 thetas that will fit within 0 to 2 pi? 4 answers. Yes, but how many answers are there to like sine of x equals 1/2? What did we find? Well, we found 2 answers, right? Pi over 6 and 5 pi over 6. So my final answer for sine of 2 theta is going to be double the number of answers that I get from my initial findings there before I plug back into the let statement or anything like that. So if I get 2 potential answers for like the linear trig equation that relates to my let statement and back to my original question, if I get 2 possible answers, I know that my possible answers are going to double when I find the maximum. Now if I keep adding pi and I get outside the range of 0 to 2 pi, that's also a good way to tell that you don't have any more answers, right? So you can keep adding pi, but it needs to stay within 0 to 2 pi if that's the range that your question gives. So if you're ever not sure, like, oh, do I have more answers? Add pi again and just make sure you're still between 0 and 2 pi. That's another way you can do it. Okay, so let's just find our last answers here. Theta 3. I'm going to do pi over 12 plus the period, which was pi. Okay, so that's pi over 12 plus 12 pi over 12, which will give us 13 pi over 12 radians. Okay, and then for theta 4, I'm going to take theta 2 and also add the period to that. So 5 pi over 12 plus 12 pi over 12 gives me 17 pi over 12. And what I was just talking about here is, let's say I tried, maybe I assumed there was a theta 5, don't write this. But if I keep adding the period, I'm getting 13 pi over 12 plus 12 pi over 12, and I get 25 pi over 12. Is that still in the range of 0 to 2 pi? Well, 24 pi over 12 is 2 pi, right? So this is now outside of the range of my possible answers. This is certainly an answer that if I plug it back into my equation will give me half, but it's not in the range that the question has given me. I'm looking for just within the first rotation for that cast roll grid. So there's no more answers past those 4 thetas. Okay? So that's not a possible answer. How do I check my answer? No, you do. Okay.
You ask God.
So I'm going to plug in each of my answers here in for sine of 2 theta. So, and I'm going to check that it's equal to a half. Okay? So this, theta 1, theta 2, theta 3, and theta 4. When I plug those into my calculator, I should get positive 0.5 out for each of those. Very important that you do get positive, otherwise you may have found something in the wrong quadrant if you get a negative 0.5. Okay, so if you plug each of those into your calculator, you're going to just do a quick little check to make sure that, sorry, this is pi over 12. You're just going to do a quick little check to make sure that you're getting positive 0.5 out from each of those. Okay, so that's your check. So I should know, beyond a shadow of a doubt, once I've done this question, whether my answers are right or not. Okay, so really it's kind of the same as yesterday. Like, we're going to solve as usual. We'll go through the decision process, and then I just need to plug back into the let statement and add the period. Okay, questions so far? We're okay? Okay, let's try one more. Cos of 2 theta equals negative root 3 over 2. We're going to do a little let statement. Let 2 theta equal, give me a variable.
J.
Not J again.
L.
Can't do favoritism here. L.
K. They're telling me that I am not your favorite.
I never said that, Jonathan. I would never say such a thing. Okay, so the cosine of some angle L is equal to negative root 3 over 2. We are going to go through the decision process. Can I use a graph to solve this?
Why aren't we using J?
Oh, we're just mixing it up a little, you know. That is a cursive L. Can I use graph? Do I have sine, cos, or tan, or sorry, sine or cos equal to 1, 0, negative 1? Probably not, no. Graph doesn't really help us. Triangle? Can I get an adjacent over a hypotenuse that gives me root 3 over 2 from a triangle? Yeah, I definitely can. Which triangle? Yeah, same one that we used in the last question. Yeah, it's half of an equilateral. That's where it comes from. So, You could call it that if you really want.
It's the other way.
No. What? The other one is just like an isosceles right angle triangle. Okay, what is going to give me an adjacent over hypotenuse of root 3 over 2? Because I have cosine, right? So I want adjacent over hypotenuse to be root 3 over 2. Alexandra?
Pi over 6.
That's right. Pi over 6 will give me adjacent over hypotenuse of root 3 over 2. So that's going to be my reference angle. It will be pi over 6. And we are going to use our nice cast rule grid that we know and love to decide where possible answers could fall here. Okay, so we're using this right now. Cosine of some angle is equal to negative root 3 over 2. Where is that going to occur? Jonathan?
Quadrant 2 and quadrant 3.
2 and 3. Very good. Sine and cosine. So we're looking for where sine and tan. We're looking for where cosine will be negative. That will happen in the opposite quadrants where cosine is positive. So here and here, where these two little slices are equal to our reference angle of pi over 6. Let's call this L1 and L2.
Wait, how do you know what quadrants we need, sorry?
So cosine here is equal to a negative value. So I'm looking for quadrants where cosine will have angles that are negative, that give us out negative ratios. So if cosine's positive here and here, then it must be the opposite two quadrants. Okay, how do I calculate L1? Jonathan?
Pi minus pi over 6.
Pi minus pi over 6, which gives us 5 pi over 6 radians. And L2? Olivia? Awesome. Pi plus pi over 6. So we're going 0 to pi and then pi over 6 just past that. That gives us 7 pi over 6 radians. Cool. So I have two answers to the linear trig equation where cosine is equal to negative root 3 over 2. If my k value is equal to 2, okay, so here k equals 2. If I get two answers here and k is 2, what's going to happen to my total number of answers when I compress by a factor of a half? Alexandra? Okay, so number of answers will double. So how many possible answers am I going to get if I got 2 from the original question? Yep. We're going to get 4 possible answers. That is likely what's going to happen, but if you had 3, it's going to triple, so then I'll get 6, right? So we're going to plug in our L's into our let statement. Don't forget about that. Plug them back in. So I have 2 pi equals 5 pi over 6. Or sorry, 2 theta equals 5 pi over 6. So theta 1 is equal to what? Jonathan?
5 pi over 12.
5 pi over 12, thank you. And for our next let statement, we'll plug in our second answer that we got, which was 7 pi over 6. So that's a potential answer, which gives us what for theta 2? 7 pi over 12, awesome, thank you. Okay, and we know we have 2 more answers. We have double the amount of answers that we got from this initial calculation here. What is the period of this? Sorry, it was cos 2 theta. Pierce?
Oh, it's 2.
That's the k value.
Oh, sorry, the k value. Pi. Apologies.
Okay, so it'll be 2 pi over the k value, which is 2, which will give us a period of pi. Okay, this is what we're going to add to theta 1 and theta 2 to get our theta 3 and theta 4. So theta 3, I'm going to do 5 pi over 12 plus pi. So that will be 5 pi over 12 plus 12 pi over 12, giving me 17 pi over 12. Are we still between 0 and 2 pi? 2 2 pi is 24 pi over 12, right? 24 divided by 12 is 2. So I don't want to exceed 24 pi over 12 for this one. So we're good for that one. And then theta 4 is 7 pi over 12 plus the period, which is pi. So 7 pi over 12 plus 12 pi over 12 gives us 19 pi over 12. Still between 0 and 2 pi? Yes. Okay, if I try to add the period to this, 12 pi over 12 plus 17 pi over 12, I've got 29 pi over 12. That's past 2 pi. So we're out of the range of the answers that we want. Okay, so those are our 4 possible answers.
So you know there's 4, because it's 2 theta, right? And then the previous graph that we looked at, the one that was summed to 2x had 4.
So I know that there's double the amount of answers for what I'll get for this, whatever that expression is. In most cases, it's going to be 2 answers, right? So then I will double the amount of answers, which will be 4. But if I were solving something like cos of L equals 1, let's just say cos of L equals -1, there's only one answer between 0 and 2 pi originally, so I'll double that and then there'll be 2. Yeah, so you just have to use your original answer there to decide on how many more answers there are. Okay, so you guys in your homework are actually going to practice one that has a triple and a quadruple number of answers here. So you're going to just keep adding the period. That's all you need to do. Okay, so you guys are going to practice a couple different ones. We're going to leave inexact values where possible. So use your decision-making process, graph, triangle, and so on. Okay.